First of all, I'd like to thank the organizers for giving me an opportunity to present my work in this conference. I'm Prajwal. I'm a postdoc at the National Institute for Gravitational Physics. And I'll be talking to you about some of the work that I've been doing with MeetCat data, particularly with globular cluster data of 2005, and some of the interesting pulsars that we're trying to find there. Okay, so my talk is two parts. First, I'll focus on one interesting binary pulsar that we found with MeetCat globular cluster data, specifically on 2005, which has found a new name called Terry, as Colin mentioned. And part two of my talk is more about trying to giving you the scientific motivation for why it's important to try and find more compact binary pulsars, and specifically delving into the kind of methodology which was used for gravitational wave searches and how it's been applied for radio pulsar searches, and how this has been scaled up using volunteer distributed computing, which is understood at home, and finally to discuss some interesting results on that. Okay, I don't want to spend too much time on this slide. I think everyone's given enough of a motivation why MeetCat is an excellent instrument for doing pulsar searching. Not only does it have a great gain, but it's also the beamforming capability which allows us to do a lot more things. And there's also specifically the targeted survey for pulsars, trying to find for pulsars with MeetCat, which is TRAPM, which targets different kinds of sources. There are going to be other different talks across these 2 days discussing specific sources. But my focus is on globular clusters. And you might ask, why do you want to search pulsars in globular clusters? Well, why not? Because high core densities compared to what you see in the galactic field, 3 orders of magnitude more, and this encourages, this makes an environment where you can have a lot more interactions, and it could lead to a lot more kinds of interesting exotic binaries which can be formed. Okay, when I gave this talk last year, we had 283 pulsars in 38 globular clusters, of which 72 were discovered with MeetCat. And luckily I saw Paulo's page yesterday and he made an update. Now it's 325. And as you can see, there are 4 new clusters. So a lot of interesting things. There are some slow pulsars also being found in globular clusters, which makes you rethink how these pulsars actually still, how are we finding these pulsars. But my focus will be on MSPs, and we also now have close to 100 discoveries with MeetCat. So if you want to know more, I would encourage you to look at these web pages. Okay, as I said, I'm going to be focusing on 2005. Why is 2005 very interesting? Because it has the most number of confirmed pulsars in a globular cluster. It has the record for that. And the work that I did with actually Paulo and others, we just got accepted in A&A, and it's already up on archive. So if you want to know more about the kind of discoveries that we've made, so we've added 10 new discoveries, of which 9 are binaries. And very interesting stuff. One could be potentially a double reversal system. Some of them are actually spider-type pulsars which show eclipses. So if you want to know more about the properties of these pulsars, I encourage you to read the paper. But my focus will be on this particular system, which is highly eccentric and shows a lot of interesting properties. So this is PSR J17.12446 or Terry, as Colin already said. So why it's interesting? It has the second highest eccentricity among recycled pulsars. There's just one more, which is higher than that. It's around 0.96. This is around 0.903. And the simplest way to explain how it acquired such an eccentricity is because you have a very dense environment in globular clusters. There's a large possibility that there are a lot of flyby encounters which actually induce eccentricity into these systems. The minimum companion mass is around 0.24 solar masses. Colin already talked about how this, his method actually made it convenient to actually solve this pulsar and eventually obtain a 19-year timing solution using also GPT archival data. To give you an interesting fact about this pulsar, this spends around 20 days having a negative acceleration and just 1 day having a positive acceleration. So it was very difficult to actually nail down a good orbital solution when trying to solve for this pulsar. Okay, so once we had this 19-year timing solution, the idea was to try and see if we can measure some post-Kepler parameters, because we have a very long timing baseline, and we tried to see if we could we could see any of these post-Keplean effects that we expect. So we did detect the rate of advance of periastron, which puts directly a constraint on the total mass, which comes to around 1.99 solar masses. Similarly, we also tried to see if we could detect an Einstein delay on the Shapiro delay. Unfortunately, this did not yield any significant detection. However, in a very special case, the non-detection of the Einstein delay led to something interesting, which is very rare, which I'll come to in the next slide. One thing we tried to do was, can we put any constraints on the mass, the individual masses, the pulsar and the companion mass? So a classic way of doing this is what you do is a chi-squared map. So you calculate the reduced chi-square of the fit of your timing solution across a uniform grid of points in total mass and cosine of the orbital inclination, which is cosine. That directly also constrains the companion mass, and you let the rest of the parameters in your timing solution you freely fit for it. Then you convert that into a probability density, and then you try to see if you can actually constrain the individual masses. So what I've plotted here is a mass-mass diagram. So as you can see, this is companion mass as a function of cosine of the orbital inclination, and this is also as a function of the pulsar mass. So the omega dot puts a constraint on the total mass, but since that we didn't have any significant detection from Einstein delay or Shapiro delay, we don't really, like from the Shapiro delay, we don't really get a good constraint. But if you look at these 1D distributions, you're seeing that the pulsar mass and companion mass are well constrained. So what happened here? What happened is you don't have gamma detection. If you come back to this equation here, what determines the Einstein delay, it's proportional to the orbital period, which is very high for TOF-IAP, eccentricity as well, which is very high. So you actually expect a high gamma value for this. The fact that you don't see a gamma value means the companion mass itself needs to be low. And that's why indirectly you're actually constraining the companion mass. And because you already have a constraint on the total mass, you're also constraining the pulsar mass. The cool result is we also have a very precisely measured, pulsar mass, which is the highest among all the pulsar masses, all the precisely measured pulsar masses in Doppler clusters. There are very few which have pulsar masses, but still it's a pretty interesting result. Okay, so that was about TOF-IAP. Now I'm going to talk about some of the searches that we have been doing with Einstein at home. So, first of all, I think I want to motivate why it's interesting to look for very compact binary pulsars. So, we already know a lot of double transverse systems as through radio pulsations, more than 20 of them. But the one which probably has the least merger time is, which has the least merger time is 45 megayears, which is this system here, PSR J1946. And from LIGO, we know that there are at least a couple of candidates for double transfer coalescences. And there's this huge gap in between. So the idea is, can we fill this gap? And we want to put our best bets, try our best to fill this gap, to try to find pulsars in this gap. So, why I already told you why it's more interesting. It's because you could do better tests of gravity, stronger fields of gravity, and put more constraints on gravity field theories. And great, where would be an ideal place to look for it? Doppler clusters, and we have very sensitive data from MeetCat. So that's one of the motivations why we started this search. Now the pulsars which I mentioned, which were found with Prajwal 5, were done with standard acceleration searches where you assume that the Doppler modulation can be incorporated by just a linear acceleration term. However, these have a lot of caveats. They only do well when the observation time is only a fraction of the orbital period. What we really want is to be sensitive to order of magnitude same as the orbital period when we have the same observation time, so that we don't have to do things like segmented searches and low sensitivity by just going for a lower T-bounds. So, I know I have very less time, that's why I just want to give some idea of how the template band methodology works. So what you do, the first thing you do is, you identify the orbital parameters and you come up with a range of orbital parameters that you want to search over. Now that's not enough, that's just the boundary. You want to ask, how do you actually fill this entire boundary with points in a more optimized way? And so what you do is, people have attempted this in the past a lot, how to do this exactly, like how to actually put templates. And what you do is, one of the things what you do is you you accept that you can't fill the entire search space perfectly. So then you ask maybe a fraction of it, I want a reasonable mismatch value, which is, yes, thank you, a reasonable mismatch value where, I'm okay with losing this much sensitivity or this much signal to noise. And so there are random template banks and stochastic template banks where once you randomly fill templates and you try to see if you're actually matching these conditions, you apply some extra pruning on top of it. But this is computationally expensive because it's quite an iterative process. So what was done was we actually reparameterized how the phase model looks like. And before, you used to have these kind of banana-shaped curves between, this is the projected semi-major axis and this is the orbital angular frequency. And because of these banana curves, you cannot actually stack them perfectly in a grid. So what we did was, because of the reparameterization, where we actually use now what is known as an acceleration and jerk, which is reparameterized in terms of the omega and x, we can actually get much more elliptical mismatch contours. So this is more efficient, it's faster to generate the grid as well, and it's more easier to generate the template bank. I think a few people already talked about Einstein at Home. So it's a volunteer distributed computing project. It's been running for many years. It's found pulsars actually, in fact, with previous surveys. And in fact, it's been upgraded like on a day-to-day basis, I would say. In fact, it's compatible with different OS architectures so that different hosts having different requirements can still run it. And in fact, we have also added Apple Metal GPU capability recently. So this is the bottom line of the slide. So if you want to help us, please do sign up. Now to the actual, some of the interesting results. So the idea was, I use the data from globular clusters, specifically 2005, M22, and M28, and we're using MeetCat data, and try to run two different kinds of searches, where we're sensitive to companions which are typically of what you see with spider-type systems or with double neutron star systems. And the results are, we know that we have been running sanity checks, and we can see that we are finding, we are blindly redetecting known pulsars, but we also have some interesting candidates. And so the focus of the future work will be to actually try and see if we can confirm these candidates. And I will leave you with my conclusions. A lot of interesting pulsars in 2005, a lot more to be found, not only in 2005, but we want to expand to more globular clusters. And hopefully we find these kind of systems which are having orbital periods of the order of tens of minutes rather than hours, what we have been doing. So thank you for your attention.
We have about 2 minutes for a few quick questions.
Oh, it's just, so yeah, I was expecting this question. Okay. So this is how the phase model looks like. So this is the rotational phase of the pulsar. F is the spin frequency. Tau is this projected semi-major axis, which is actually X here. Sorry about that, I should have changed that. And omega is the orbital. This is a function of, this is 2 pi by orbital period. And this is the initial orbital phase. So the previous template bank just used to use this. And if you look at these terms, and if you look at this term here, if you look at this term, you have tau omega square. So for a constant acceleration, tau and omega square actually degenerate. And if you translate that to a plot, this is how it would look like. That's why you have these kind of banana curves. You have this kind of a parabolic trend. So what we did was, we applied this parameterization. You apply A equals to omega square sine, is it phi or psi? I'm always confused with that. Okay. And J is tau omega cube. You actually rewrite the space model this way. And to at least, the first few terms, this effect goes away. Because you now have a reparameterization. You now have it in terms of acceleration and jerk. And so if you plot acceleration versus the omega, you actually get elliptical contours.
But this is not orthogonal, right? It's not an orthogonal. You didn't divide it as orthogonal polynomials, like Chebyshev polynomials.
No.
Question over there?
Yes.
Or at
42.
least 42. And,
It's the answer to everything, yeah.
and
Oh yeah, sure. So it's just about constraints. So actually we would like to. So what we are doing is, so if I get back to maybe
currently you have covered 3 clusters.
3 clusters. So the idea is, so TRAPM, the TRAPM globular cluster group has been observing a lot more number of globular clusters. So at least for a start, we want to incorporate those globular clusters as well, because people have run standard linear acceleration searches on those and found pulsars already. But we are a high risk, high reward game here. So we want to go through all those clusters again and try to see if we can find pulsars. So that's the start. But then eventually we would like to expand to everything else.
Okay. We're kind of running out of time for questions, so yeah, we can probably discuss later. So thanks again, Prajwal.